Hey all you cool cats and kittens out there. Today I am going to talk to you some more about NMR spectroscopy. So remember we had 4 different features of NMR that we were going to look at. The first one was number of different signals, which we talked about in the last video. Now I want to talk about chemical shift. And if you remember, basically what chemical shift does, it's that x-axis on the XY scale, and it basically, tells you something about the neighboring environments of whatever proton is causing your signal. All right, so we're going to be basically seeing reasons here why certain signals are a little bit further upfield or certain signals are a little bit further downfield relative to each other. All right, so what I'm going to do is I'm going to sort of harken back to this, some of that background theory we talked about. When we have the individual nuclei, the individual hydrogen nuclei, and they are brought into contact with a large magnet, right? And we said that, they can align either with or against the magnetic field. And if we have one aligned against the, aligned with the magnetic field, I shouldn't have drawn that arrow like that, right? We said that, if we bombard it with radio waves, we can cause it to spin flip, right? So one thing about these spin flips is that, not all nuclei are created equal when it comes to spin flips. Some of them are really, really easy to get to spin flip up. Some of them are going to be much more difficult, all right? And depending on if they're easy or difficult to spin flip, that will determine the type of energy, whether it requires high energy radio waves, low energy radio waves, or somewhere in between to get it to actually spin flip. All right? So here's a good analogy for thinking about this. Whenever this magnet comes into contact or proximity with your nucleus and causes it to sort of rigidly line up in place, you can have a couple of different situations. All right? Think of it as a nail in a wooden board. All right, sometimes you can have your nail in your wooden board, and I'm going to represent this with the nucleus, and it is very rigid, very rigidly held into place, right? You can't wiggle it. It's hammered in tightly, okay? Or you might have another nail that's been, in a piece of wood for a long time or something, and maybe the hole has gotten a little bit contracted or something, and it's a little bit wiggly. And I'll sort of put these little motion lines around it to represent the fact that it's wiggly, right? Well, think to yourself, is it going to be easier to just with your fingers pull out the nail that's held in rigidly, or the wiggly nail? I think most of you would probably say, yeah, it's going to be a lot easier to pull out the wiggly nail, all right? This analogy works very, very well for talking about nuclei and their tendency to spin flip, right? Wiggly, quote-unquote, nuclei are easier to spin flip. And because they're easier to spin flip, they require lower energy radio waves. All right. To get a rigidly held nucleus to spin flip, you have to blast it with a pretty high energy radio wave to get it to flip up, right? And this is going to manifest itself on your chemical shift scale, right? The nuclei that take more energy, the higher energy radio waves, they're going to appear further downfield. The ones that are lower energy, they are going to appear further upfield. Just make a quick note of that here once I get everything erased. I'm sure there's probably a way I can clear this all off of my screen at once, but hey, guess what? Haven't found it yet. Alright, so higher energy downfield. The ones that require lower energy waves are further upfield. All right? So, that's how you can sort of recognize, why something's upfield or downfield. But what about the root cause of this? What causes, a particular nucleus to be more rigidly held in to a certain spot, or maybe be a little bit more quote-unquote wiggly? Well, it all has to do with its neighbors. All right? Again, I'm going to draw just a nucleus here. All right, and remember, the nucleus has a magnetic field not only holding it in place here, but a nucleus has its own magnetic field. Don't forget, within a hydrogen atom, you do have one electron, and this electron orbits around the nucleus, right? And that creates a magnetic field. All right, we'll call this one nucleus 1. And it's got its own field. Well, it can have neighbors, right? Let's say we have a different group of hydrogens here, a different type, chemically non-equivalent. We'll call this one nucleus 2. Yeah. Well, that was really ugly. Sorry about that. All right. Now, nucleus 2 has its own magnetic field separate from nucleus 1, right? Nucleus 2 is a different type of hydrogen, but it still has an electron floating around it that creates a certain magnetic field. Basically, what happens here is that the magnetic field of nucleus 2 sort of interferes with the overall magnetic field externally that we put in. All right? It diminishes the effect of it. Right? So if a particular nucleus has neighbors around that are sort of interfering with this external magnetic field, then its overall effect is lessened. All right? In other words, nucleus 2 kind of makes nucleus 1 here wiggly because it's not as held into place as it would be if nucleus 2 wasn't there. All right? What we say here is that nucleus 2 provides shielding. In other words, the magnetic field from neighboring protons helps to shield the neighbors from the big external magnet. All right? And as a result, they don't feel the external magnet quite as much, and they're not quite as rigidly held into place. Right? So, if you have something that's really, really shielded, I'll see if I have enough room here to write this. If you have something that's shielded, that means it's easier to flip. Which means it's going to require lower energy on your chemical shift scale, and it's going to be further upfield, right? The more shielded something is, the further upfield it is. All right, now conversely, there are other things, there are other factors that can be present within a chemical structure that basically remove the effects of neighboring nuclei, right? So that nice little shielding effect that you have from your neighboring protons, sometimes that gets taken away by other stuff in the environment, right? This is a situation called de-shielding. And that's just the opposite of shielding. De-shielding is going to, a proton that's de-shielded is going to be harder to flip. Which means it's going to require a higher amount of energy, and it's going to be further downfield. Okay? All right. So let's take a look at some of the let's take a look at the factors here that actually cause shielding and de-shielding, and therefore play an impact on where your particular signal is going to show up on a chemical shift scale. All right. All right, first of all, let's look at causes of de-shielding. That's going to be probably the most important one. All right. Basically what happens here, one way that we can cause de-shielding is to interfere with the neighboring electrons, right? We said it was because of the neighboring nuclei's electrons that, we got that sort of shielding effect. What would happen if we maybe pulled away those electrons, right? We kind of drew away our neighboring electrons. If we drew away the neighboring electrons, then we're not going to get as much of a shielding effect, right? So think to yourself, what can pull away electrons or electron density? And this is something we've talked about a lot. The presence of electronegative atoms. Basically, you get an inductive effect here, right? So you have one of these greedy electronegative atoms that likes to pull electron density to itself. It can pull the electron density of a nuclei's neighbor, and that will, in fact, reduce the shielding effect. All right? So, generally speaking, the closer that your proton is to something electronegative, the more de-shielded it is. I'm just going to use the term Z here to refer to anything electronegative. Generally speaking, the closer to Z, the more de-shielded it is. All right, let's take a look at an example. All right, and I'm about to show you a few sample NMR spectra. And so I'm going to click off of whiteboard here for a second. And I'm going to direct you to a website that I really like a lot. It's really cool. Really good place to look up spectra. Just go to Google and put in SDBS. And probably the first thing that'll come up is this AIST spectral database for organic compounds. All right. Really, really good. Allows you to search, and it has a number of different spectra, IR, NMR, and plus several we haven't talked about yet. All right. So I'm going to pick one here. I'm going to put in to the search bar 1-bromopentane. All right, and I'm going to pick the HNMR. And unfortunately, I cannot draw on this with my stylus, so you'll have to listen to my instructions here to sort of look at the different signals. This is the proton NMR spectrum of 1-bromopentane. All right, and so you can see the picture with the squiggles on the page, and also you can see a structure drawn down below. And below that, you see that the H's are labeled A, B, C, D, and E, and the page here tells you what chemical shift parts per million each one of these signals appears at, right? So it's very nicely laid out. You'll notice we do have an electronegative atom here, right? We have a Br, all right? And then so it's, you have sort of increasing distance away from this Br, right? So if we look at the one that's closest to the electronegative atom here, that's going to be signal A. And you can see signal A has a chemical shift of 3.398. That's going to be that big sort of cluster of, looks like maybe 3 peaks over here, farthest to the left. All right, and that's what you'd expect here. This signal is closest to the electronegative atom. It's going to be the most de-shielded, and therefore it's going to appear furthest to the left, or furthest to the downfield side. As you get further away from the bromine, right, you see signal B is further upfield at 1.86. Signal C and signal D, they kind of overlap each other. They're at 1.44 and 1.32. Signal E is going to be the one that's furthest away from your BR, and it's also the one that's furthest upfield, right? So you can really see here the effect that the proximity of electronegative atoms has on your signal. Closer it is, the further downfield it is. All right. You could also look at the number. The number of electronegative atoms is going to be important, right? If you had 2 BRs that were very, very close to a particular signal, it would probably be pretty far downfield compared to the rest of the signals. Okay. Let me show you another one. So let's see. Return to search. All right. This time I'm going to look up 2-pentanol. All right. And here's the NMR of 2-pentanol. And we can see much the same thing. All right. There's the spectrum. There is the structure. Come on. I'm trying to get my keyboard to go away. There we go. Okay, so you can see here's the spectrum, here's the structure, and then here's the assignments. All right. So you see here we have an oxygen, and we do have an H directly attached to the oxygen. You do see de-shielding of proton signals that are directly on electronegative atoms like oxygen and nitrogen. Curiously enough, it's usually not quite as much as it is. It's not quite as evident in the ones directly attached to electronegative atoms as it is to the ones that are directly neighboring. So in this case, you see signal B is de-shielded a little bit. It's at 1.92, but it's not quite as de-shielded as signal A is. So that's a little quirk. The ones that are on carbons directly adjacent to the electronegative atom tend to get de-shielded a little bit more than the ones that are directly attached. But you can see here, the signal A, which is CH, that's going to be the furthest one downfield at 3.79. Then it's going to be signal B, which is the one that's directly attached to your oxygen. Signal C is going to be the next one. Signal D is pretty close to that, and then signal E is the furthest away, so it's going to be, again, the furthest upfield. Right? So you can see definitely a noticeable correlation to proximity to the electronegative atom and whether it's going to be further upfield or downfield. All right. So that's one thing that can cause de-shielding. Another thing that can affect the shielding or de-shielding capabilities is the presence of pi electrons. All right, you think of pi electrons, really you think of four major cases, right? You think of aromatics, you think of alkenes, you think of alkynes, and you think of carbonyls, C double bond O's. There's other ones, but there's other situations, but these are the major ones, right? And basically what happens is whenever you have these pi electrons, they swirl and they make, yet again, their own magnetic current as well. And this magnetic current can either enhance the external magnetic field or it can oppose it. In other words, it can make the effects of the external magnet stronger or it can make it weaker. All right? Certain ones tend to do certain things. These are called anisotropic effects. Fancy schmancy way of saying the effects of pi electron magnetic fields on the external magnet. Come on. There we go. All right, and as far as the ones that cause de-shielding, A, aromatics. The closer an H is to an aromatic group, certainly the more de-shielded it is, because the aromatic pi electron system enhances the external magnet. You also see this with alkenes, and you also see this with carbonyls. So three of the major groups will serve to cause de-shielding and cause the signal to appear further downfield. All right. So again, let me kind of look over here, and let's look at a couple of sample spectra, so you can sort of see the evidence of this. Come on. There we go. All right, so this time I'm going to search for ethylbenzene. We're going to do an aromatic. here's ethylbenzene. All right. So again, you can see the spectrum here, as well as the structure and the group assignments. All right. You see that we have 5 H's that are on this aromatic ring. These are all aromatic H's. They are, of course, closest to that aromatic magnetic field, and so group C is definitely going to be the most deshielded here, right? It's very, very strongly. In this case, you have a cluster of peaks between 7 and 7.45. All right. Here's a healthy tip. Whenever you're looking at NMR spectra, if you see a signal between 6.5 and 8, that's almost a sure bet that that's going to be an aromatic group, because that's really the only thing that tends to absorb in that region. Pretty far downfield, sticks out like a sore thumb. All right. And then you have 2 other signals here. You have signal B, which is the benzylic group of H's. All right, and you see signal B is 2.63. Signal A, which is the methyl group, it's going to be at 1.22. So as you're getting further and further away from that aromatic field, then you're getting a weaker deshielding effect, and the signals move further upfield. All right. Let's take a look at an alkene. So let's take a look at cyclohexene. Okay, here's cyclohexene. You can see much the same thing here. If we look at the assignments, we have 2 H's that are directly on your alkene group, so they're the closest to your carbon-carbon double bond. These are both, these H's are deshielded quite a bit. They're further downfield, about at 5.6. The signals for that belong to group B are a little bit further away, so they're upfield at 1.98, and the ones furthest upfield are the ones belonging to signal C at 1.61. They're the furthest ones away from your alkene group, so that makes sense that they would feel the least amount of deshielding effects. All right, let's take a look at one more. Sometimes the website times out and you have to start over. Not a big deal. All right, let's see. Let's look at an aldehyde. Aldehydes are interesting because, let's see, which one do I want to look at? Let's see if butanol is in here. Butanol, also known as butyraldehyde. There it is. Yeah, here's the one for butanol. And you'll notice here, if you look at the aldehyde H, right, this is the word, a signal A, where you see the CHO. Aldehyde H's are very, very far downfield, right? They're very, very deshielded. They're deshielded not only because you have the pi bond of magnetic field, but you also have an electronegative O that's very close by. So aldehydes tend to get isolated very, very far downfield, usually around the chemical shift of 10 or so. All right, and again, as you can see, as we descend further and further away from your aldehyde group, B, C, and D respectively, we get further and further upfield. All right, so you see there's lots of things that can cause deshielding of signals, of hydrogens, and cause signals to go further downfield. Now, conversely, there's not much that really causes shielding effects. There's really only one major group. And that's alkynes. The carbon-carbon triple bond happens to oppose the external magnetic field in an NMR, so these actually give you a bit of a shielding effect. So you would expect, you know, alkyne signals to be located more on the upfield side of things than the downfield. All right. Just like we had a correlations table with IR, you can have correlation tables with NMR as well. Just look in your books or look online. You can find them all over the place. Here's just one I happened to Google. And you can see, right? Just like with IR, you can correlate certain types of groups very well with certain positions on the chemical shift range. You can see the ones that we would expect, you know, to be downfield. Aromatics, right? We said, you know, I said about 6.5 to 8 or 6 to 8.5, you know, somewhere in that range. You would expect those to be a bit further downfield. You would expect the presence of halogens, like you see in the middle, to cause a bit of deshielding. So they're like, you know, closer to the 3 to 4 range. You see with this alkyne group, however, you know, they're a little bit further upfield, where it says acetylenic. You know, the chemical shift of those is about 2 to 3, right? So a little bit further upfield than some of these other ones. One thing I want to notice in particular is the carboxylic acid, which is the second one from the bottom. Those groups are extremely deshielded. In fact, they usually appear at about 12, 12.5 or so, because not only are they close in proximity to two O's, but also they're close in proximity to a carbonyl pi bond. So the two that really, you know, tend to go really far off scale quite a bit that we see a lot of are aldehydes and carboxylic acids. But yeah, definitely use these, you know, chemical shift scales to help you as you interpret your spectra in the future. All right, that is going to be it for right now. Next video, next NMR video, we'll focus on integrations and how we can use that to figure out ratios of different signals to each other. Until then, hope you have a good day.